Rolling, yeah, okay. 1.2 now are the basics of functions and their graphs. So let's take a look. So 1.2, basics of functions and their graphs. Okay. So to understand what a function is, we first need to know what a relation is, and a relation, just very simply, is a set of ordered pairs. So a relation is a set of ordered pairs. Okay, and in that, any graph that any equation that you do, you can think of as a set of ordered pairs. So the absolute value thing we looked at last time is a relation, very simply. Okay, so sort of defining this relation, we have a domain and we have a range. Okay. The domain is going to be the x coordinates, or the x components of your ordered pairs. And your range are the y components. We'll just put x and then y. Okay, so let's look at number 2 in the book. They give us a relation, so 4, 5, 6, 7, 8, 8. And they want you to identify the domain and range, so we'll just write D for domain and say that equals the set 4, 6, 8. No big deal there. Then range, we'll just say that equals the set 5, 7, 8. Okay. An alternate way of describing the set of ordered pairs, describing this relation, is through an arrow diagram. And so an arrow diagram, basically all you do is draw these two ovals, and then put little points for each guy in the domain. It's probably a good idea to label those points. So 4, 6, 8. And then over here we do the same thing, but now we use the range, right? So 5, 7, 8. And then we draw arrows from the x to the y part. So I go from 4 to 5, I go from 6 to 7, and then 8 to 8. So 4 to 5, 6 to 7, and then 8 to 8. Okay, so again, this is the domain, this is the range, and this thing happens to also be a function. Okay, it's a relation, but in particular, it's a special kind of relation called a function. Okay, so if you want to define what that function is, okay, so function, and here each member of the domain corresponds to exactly one member of the range. And usually this definition is kind of hard to visualize, so what we do is give you an example and kind of hopefully you'll understand. And generally they'll show you with these arrow diagrams. So an example of a non-function is usually a little more instructive. Okay. So we'll say we have 3 elements in the domain and 2 in the range. And we're sending this guy here. Well, maybe we should put a couple more. This guy will send here, this guy's in here, that's no problem, right? So each member of the domain has exactly one member in the range associated with it, but the problem becomes when you take one guy here and then send him to a different guy over here. Okay, so you can't have this kind of splitting from your domain. You can't have one guy going to two separate places. And in the set sort of relation version, the set version here of the relation, what you'll see is a repeated x coordinate. So you'll see like 4 repeated twice, and that means it's not a function. Okay. So let's look at one in the book. The one in the book's a bit overkill, but we'll take a look. The number 4, we have the point 5, 6, and then 5, 7, and then 6, 6, and then 6, 7. Immediately from what I said above, this guy's not a function, and it's because you have 5 going to 6 and 5 going to 7. And on top of that, you also have 6 going to 6 and 6 going to 7. So it's really, in my opinion, it's overkill. It's not a function. Now, one small point. Okay, so this guy, let me just note that's not a function. You can have the problem in the other direction, right? So what do I mean by that? You can have a relation that is a function such that you're having more than one guy in the domain go to the same guy in the range. Now that's not a problem. See, this thing right here is going to be a function. Okay, this isn't the issue. It's this that's the issue. Okay. This is a function. It's fine. In our work, we're generally not going to be looking at just these kind of scenarios where you have a finite number of items in your relation. What we look at are equations, of course. Equations represent sets of ordered pairs. It's 3 functions as equations. And you can usually tell if something is going to be a function or not, because you'll be able to solve, if it is a function, you'll generally be able to solve for it explicitly. So you'll be, when I mean explicit, y equals something. Okay, that's a good thing. So solve for y, and then see if you can, basically. So for number 11, we have x plus y equals 16, right? I can solve this for y with no problem. So I have y equals negative x plus 16. And this guy is a function. So we compare that problem to number 16, which we have the equation x squared plus y squared is 25. And this character right here is the equation of a circle, right? Okay. Visually, we know that's not going to be a function. We'll talk about that more later. We have the vertical line test, right? But just for right now, in this sort of program, what we're doing is trying to solve for y. So if I solve for y, I'll have y squared equals 25 minus x squared. And then I'm going to use a square root property, which causes the trouble. So when you see this plus or minus thing pop out, so I have y equals plus or minus 25 minus x squared. When you see this character rear its ugly head, you know that's trouble, and it's not going to be a function anymore. So for any x I put in here, I'm going to get out 2, well, almost any x, right? If you put in 5, you only get out 0, but anything within the domain of this function, you're going to get an output of 2 numbers. Okay, so this is not a function, and if you're just totally blown away, it's because of this. It's because of the plus or minus. Okay? The square root property. We have to put that plus minus in Okay, let's look at 26. So here we have an absolute value guy. It's absolute value of x minus y equals 5. This looks more complicated, but it turns out it's also a function. I can solve for y with no problem. Y equals absolute value of x minus 5. Okay, and this is just going to be one of these 1, 2, 3, 4, 5. One of these V shapes, okay, at the end of the day. Okay. I want to work a bit with function notation. So the idea in function notation is they always give you this picture of a machine. Okay, so there will be a function with a name, something like f, and then you have things coming in, you have things coming out. So the things coming in will be your input, or the independent variable, your input x. Okay? And then the things coming out will be your dependent variable, f of x. Okay, so the book will focus in on evaluation of functions using function notation. So the way it was probably introduced in basic algebra is, before we had equations like y equals 3x plus 2, and now we're going to write it with function notation as f of x equals 3x plus 2. Okay, so we want to evaluate some of these functions at certain x values and then simplify. We have problem 28. F of x equals 3x plus 7. They have part A, B, and C. So part A, they want you to put 4 into that function and evaluate it. So wherever you see an x, you're going to put this 4. Okay, so you'll have 3 times 4 plus 7. 3 times 4 is 12. Okay, so you have order of operations, you have to follow. Plus 7, and that's 19. Okay. So with numbers, it's not that big of a deal. You certainly can make it really complicated by throwing in some algebraic expressions, but you can handle it. So I'm going to replace x with parentheses x plus 1. I use parentheses when I put it in there to remind myself that I have to distribute. So it's not just 3 times x. It's 3 times x plus 1. So to indicate that, use these big parentheses. And then plus 7. They want you to simplify it. Right, so you have to distribute the 3. And then that'll be 3x plus 10. Okay. We'll be doing a lot of tests for symmetry coming up, so we need to be able to do things like part C. So f of negative x. I want to put negative x in for x and see what happens. So in this case, I'll have 3 times negative x plus 7. 3 times negative x is negative 3x, and then plus 7, and that'll do us. Right? Let's look at a bit more hard, more difficult example. So look at number 30. Okay, this time they're giving us a quadratic function. G of x is x squared minus 10x minus 3. Okay, and then I'm going to zip through and first evaluate it. Okay, so g of negative 1, negative 1 squared minus 10 times negative 1 minus 3. Okay, you have to put this negative 1 in parentheses. And the big deal back in basic algebra is the fact that negative 3 squared is not the same as negative 3 in parentheses squared. Right? These are different things, and if you write it this way, I'll mark it wrong, even if you get the correct answer. So a lot of people get upset. Ooh, I got the right answer. Well, you got lucky, and I don't give points for luck. Okay. Okay. So negative 3 squared is actually negative 3 times 3, which is negative 9. And then negative 3 squared is negative 3 times negative 3, which is then positive 9. Okay, so there's a big difference. Okay, so back over here, negative 1 squared is 1. Here we have a negative times a negative, so plus 10, then minus 3. So I have 11 minus 3, which is 8. Okay. So that's good. We all need to know how to do that. But what's more important is going to be this put in negative x instead of x. Right? And we'll follow the same sort of procedure. So I'm going to replace x wherever I see it with parentheses negative x. Okay. And then I'm going to simplify. Now again, you need these parentheses because you don't want to accidentally say something you don't mean. So negative x squared is x squared, and then negative negative is positive 10x, and then minus 3. Okay. What else? Well, sure, let's look at part B, g of x plus 2. So again, I'm just replacing x with this thing, x plus 2 in parentheses. Okay, I'll probably have some foiling to do, that's always fun. So x plus 2 squared minus 10 times x plus 2 minus 3. Okay. Zip through there and FOIL x squared plus 4x plus 4. Distribute minus 10x minus 20 minus 3. Combine some like terms. You got x squared 4x minus 10x is minus 6x. And then I have 4 minus 20 is negative 16. Minus 3 is negative 19. Okay, okay, great. Let's go ahead and move ahead. Look at some graphs of functions. Okay. So finally, if you've been holding your breath, we could talk about the vertical line test. Okay. Graphs of functions. Again, you could use point plotting to pull this off. For now, we'll learn different methods later, just by moving graphs around in the XY plane. So, but first, point plotting is always a great way to get things done. And the book will want you to do some comparisons of things that have pretty much the same equation, right? So some comparisons. And in particular, number 44, they want you to compare these two parabolas, f of x equals x squared, and then probably g of x is x squared minus 2. Okay, I'm going to do some t-tables. So for f of x, I'll have x and then x squared. I sort of know what I'm doing, so I'm just going to pick some points that I know that are important. So negative 3, 0, and 3. And then for g of x, I'll pick the same points. Okay. So when I plug these in, what I get? Negative 3 squared is 9. Okay. 0 squared is 0. And then positive 3 squared is 9 again. Here we have negative 3 squared is 9 minus 2. Okay. So positive 9 minus 2 is 7. And then if I put in 0, I get negative 2. And then 9 minus 2, I get 7 again. So you can kind of see the y values are all being shifted down by 2 places. And we're going to see that in the graph once we go over to the graph. So let's go ahead and get this set up. Need about 1, 2, 3 tick marks on the x-axis, and I think like 9 on the in the positive y direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll need at least 2 in the negative y direction. Let me start graphing. I'm going to do f of x first, and negative 3, and then 9, 0, 0. And then 3, 9, and this is going to have like a curvy shape, so it's not an absolute value function, rather it's parabola. Okay? It's not. It doesn't have a corner on it. It's smooth. Okay. Okay. So for this guy, then what happens to the graph? Well, I said the y values are all being, so it's being shifted down by 2 places. So let's take a look. So -3 and then 7. So literally this point got shifted down 2 places. 0, -2, it's right here. It's getting shifted down 2 places. And then 3, 7. And again, that happens. This is going down here. So we'll go ahead and graph that guy. Like that. But I want to label this. This is so your reader knows what happens. And you know what I've been told is you always want to do things as though you're kind of explaining it to somebody that's 2 weeks behind you in class. So if they would, so you imagine you have a friend who starts off in a 14-week class. You're in the 16-week class, and you're trying to explain it to them. Okay. So you want to think, okay, can somebody actually read what I'm doing? Does it make any sense whatsoever? I've seen students who just throw a bunch of stuff at the wall and see what sticks. And it's not a good approach. It's bad for the person reading it. It's bad for you too, because it will be unorganized and kind of hard to funnel into your brain. You want to organize it as you're putting it out there in space. Okay. So finally then, once we have this all established, doing a little bit of graphing, we can introduce the vertical line test for functions. And here we have example 6. We have some particular drawn out graphs for us. I believe the first one is an ellipse. Okay. And the second one is the equation of a line. And the third one is a sideways parabola. Okay. So you don't have to have parabolas always going up or down. You can have them going left or right as well. So a relation is a function if for each x value there's only one corresponding y value. So if you go here and look at this x value, there's 2 corresponding y values, and that makes it not a function. So you could use this vertical line test to show that. Basically, if any vertical line you draw ends up hitting the graph in two or more places, it's not a function. So here I have a vertical line I drew, went through the graph in 2 places, so it's not a function. Okay. Certainly there are vertical lines I can draw that don't even hit it, but we're talking any vertical line. So sadly, this one hits it in 2 places. It's not a function. Okay. This guy, on the other hand, you can draw a vertical line anywhere you want, and it's only going to hit the graph in 1 place. Okay. So equations of lines are always going to be functions. And that turns out to be true, I believe, for any polynomial. That will be true. Okay. This guy, sadly, again, it's going to fail. Draw a line through here. It hits it in 2 places, so it's not a function. We'll work a lot with functions. Don't be misled, though, because non-functions are very important as well. I mean, look at this thing. Can you imagine a world without circles and ovals and stuff? No, math has to sort of, math is a way of handling this external reality, and we model this external reality. So in our mathematical models, you can expect we're going to have some ovals and circles. We're going to be dealing a lot with non-functions. Okay? So it's a bit misleading in these early classes. You'll be, oh, everything's a function. No, that's not true. We'll want to work exclusively with non-functions a lot. Okay? Okay, so just a warning for future. Well, once we get that, the book wants us to work with domain and ranges now, so we worked with that. It's a lot easier, obviously, with sets of ordered pairs. But if you have the graph of the function, they're hoping you can just sort of look at it and know what the domain and range is. Right, so it has some examples from the book, basically. 78, let's take a look. We have a parabola. It's x-intercepts negative 3, 0, and 1, 0. And then on the y-axis, or sorry, on so the vertex is negative 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. That goes like this. Okay, we need to identify the domain and range. So kind of what I do for the domain is just draw a number line underneath the drawing, the graph, and think about all the possible values, or maybe even think about, think about a shadow, right? So imagine there's a sun up here casting a shadow. And what would the shadow be on this number line? Everything would be sort of shadowed in. Okay, so the domain here would be all real numbers. We're going to do a bunch of examples. So if you didn't get that, hopefully you'll get the next one. Right, the range would be kind of the shadow in this direction. So you can imagine maybe you have a headlight scenario going on, like a car. And it's casting a shadow this way. Well, the range will be all numbers up to 4 and including 4. Okay, so it's all of this stuff down here. You can see above it, there's no points. Right? So the range over here would be from negative infinity to 4. Let's try another. We have 80. So this time it's an absolute value function. The x-intercept is at negative 1, 0. The y-intercept is at 0, 1. And then it kind of goes like this. Okay, so it's a big V shaped. Again, like the parabola, the domain is going to be all real numbers. Okay, so for any x value, there's going to be a corresponding y value. Then for the range, it's a little different, right? So the range in this case, there's no points down here. There's no y values in this direction. There's only y values in this direction. Okay? Again, you think of it as like a shadow if you wish, but it's going to go from here on. Okay, so the domain is negative infinity to infinity. The range is 0 to infinity. Let's try another. There's 82 in the book. So I should probably start with these. These are a little more clear, although they're not your typical kinds of graphs. My first point, 0, 3. 1, 2, 3. And then my other point, 1, 2, 3, 0, negative 4, 0. 2, 3, 4, 0. And then I have this point out at negative 6, 4. So it's like this. The graph looks like that. Okay, so another way I would talk about figuring out the domain and range is thinking about trash compactor. Okay, so imagine this is stuck in between a trash compactor and it's smushing it onto the x-axis. And you can see the residue left over would be your domain. Yeah. So 0, 1, 2, 3, 4, 5, 6. You have all this smushiness left over for your domain. This open dot means it's not included. Okay, so we would have a parentheses here. This closed dot means it is included. So the domain would go from, I should have labeled this is at negative 6 here. The domain will go from negative 6 to 0. And then likewise, you can imagine a trash compactor here, smushing it in this direction, and then your sort of residue left over would be like that, and that would give you your range, which I've been putting on this axis over here to the side. So let me be a little more careful this time, actually put some tick marks on there. So it's -3, 0, 1, 2, 3, 4. And then basically I'm just transferring all of this onto here. Okay, so the range in this case, -3 to 4. Okay, let me give you one more for the road. Let's see. This is 84. So I have a point at -1, 0. I have a point at 0, 1. And then it just keeps going up. Okay, so it's just going to keep going up and up and up and up. Okay, so again, I like the smushing idea. So smushing it onto the x-axis will get our domain. It'll look like that. So it's including -1, and then it just keeps on going on and on forever. So the domain is going to be -1 to infinity. And then again for the range, trash compacting it onto the y-axis. So it's going in this direction. Or if you wish, you can draw it over here like that. You want to be a little careful, right, with it. It's not -1, it's actually 0. Okay, so it's starting at 0 and then going to infinity. And that's the range. Okay, and then I'll do it for this section.